So, did this video a few months ago, but we're going to update it now. If we got a function, y is a function of x, and this is just a generic graph, we want to know what the derivative f dash of x is. And first, this is sort of an informal definition, but f dash of x is just equal to the gradient of f of x. And then we can actually take a second derivative, and pretty simple notation, we just put f double dash of, and that's equal to essentially the gradient of the gradient, so the rate of change of f dash of x. Some notational issues. F dash of x is equivalent to writing dy by dx when we've got y as a function of x, and f double dash of x would be equivalent to writing d2y dx squared. These are just notations, so these mean exactly the same thing, and we'll see this later. We'll use them interchangeably. Now we're going to think about different values of f dash of x and see what that tells us. So if f dash of x is greater than 0, well, remember this represents our gradient, so that just means that we've got a positive gradient. Alright, and similarly, f dash of x is less than 0, this implies we've got a negative gradient. So this just means the graph is going up, and this just means it's going down. Sorry, that had a little bit of a positive gradient, but anyway. So there's another negative gradient, or that even. Whatever, there's loads. You could have this, anyway. And for these, yeah, it could be a straight line, could be a really steep gradient, could be something really shallow to begin with. They're all positive gradients or negative gradients. Remember, gradients between left to right as x increases. And then our final case is if f of x is equal to 0, and this gives us 0 gradient. Sorry about the handwriting there. My pen just glitched out. Anyway, 0 gradient, and we call this a stationary or even a turning point. So that's if you got a graph here, it's this point here where your gradient is equal to 0, where it's going from positive to negative. So how do we know if our turning point's not like this or like that? Well, this is when this function becomes useful. If f double dash of x is less than 0, this implies we have what we call a local maximum. So it's the greatest y coordinate on the graph in that sort of y, like this graph per se. That's a local max, but the graph might go like this, and there's still a point higher, but this is still what we call a local max. Now, if f dash of x is greater than 0, we get a local minimum. Okay, and in other videos we might look at what happens when this is equal to 0 and why we get local max and mins, but for this whole summary, this will suffice. on screens the formal definition for f dash of x. You take the limit as h goes to 0 of f of x plus h minus f of x over h, and I'll show you where this comes from fully in a video. It's pretty simple to understand, but for this video we'll just do a summary. You might think if we're taking the limit as h goes to 0 and h is on the bottom, well, surely nothing has a derivative. You know, if h goes to 0, you can't divide by 0. But remember, it's the limit as h goes to 0. It's not h equals 0. You can do some rearrangement so that when you take this limit, depending on what the function is, you will get a derivative. But for some things don't have a derivative, some functions don't. But next up I'll show an example of how to get a differentiation result. It's pretty well known using this formula. Right, I'm going to take the example of when f of x is equal to x to the n. So from our formal definition, f dash of x is equal to the limit as h goes to 0 of it, and we'll just substitute this in, so it's x plus h to the n, because when we do f of x plus h, we're taking our input as x plus h, so we've got it's not x to the n plus h, it's x plus h all to the n minus x to the n, that's our f of x, over h, right? Now we're going to do the binomial expansion on this, and we're just going to ignore the limit for a second, we'll bring that back in later. So just this fraction becomes x to the n plus n factorial over n minus 1 factorial times 1 factorial, but that's just 1, of x to the n minus 1 times h plus n factorial over n minus 2 factorial times by 2 factorial, and then xn to the minus 2 h squared, and we keep adding terms till we get to just h to the n, and we've still got our minus xn, and that's all over h, right? These xn's clearly cancel each other out, and this h on the bottom cancels with all the h's, so that thing goes to 1, that thing goes to n minus 1, and then what we find is this is the only term now that has no h term in it, because this one had h squared, the next one had h cubed, h4, be up to h to the n. So when we divide by the h, this is the only one left with no h term. Now we take the limit as h goes to 0, so all these terms with h in disappear. Alright, so we are just left with f dash of x is equal to n factorial over n minus 1 factorial x to the n minus 1, and this looks a little bit complicated. I've left the 1 up just because we know that's equal to 1, but we look, n factorial is just equal to n multiplied by n minus 1 factorial. So these n minus 1 factorials cancel each other out, and we just get that this is equal to n multiplied by x n minus 1, and this is a very common result, but now you can see where it comes from what we call first principles, or the definition of the derivative. Just just quickly we're going to go through some common results and also see the dy by dx notation. So if y is equal to e to the x, then dy by dx is also equal to e to the x, which is very useful. But, and now the opposite of the inverse of e to the x, y equals ln x, and this differentiates to 1 over x. Now we'll just go on to sine and cosine. So y equals sine x leads to a derivative of dy by dx is equal to cos x, and then finally y equals cos x means dy by dx to minus sine x. And you can try and maybe solve all these yourself now. The first principles we saw on the last page, I haven't been through them in a while, so I don't know how difficult they are to prove. I think these sine and cosine functions are pretty easy ones if you want to try them. Yeah, and you can see how sine and cosine cycle round. If sine differentiates to cos, then you differentiate cos to sine, well then minus sine differentiates to minus cos, and you just keep going like that. But that's it for our common functions. We'll now go on to the chain, product, quotient rules, and then finish on some implicit differentiation. Let's have a quick look at the chain rule. The chain rule you use when you've got a function inside a function. So the rule itself is that if you've got dy by dx, that's equal to dy by du over du by dx. And the reason this is useful, if you've got a function u, you can then differentiate that with respect to x, and differentiate y with respect to u, and then find dy dx like you desire. So the example we're going to use is we're going to take y equal to e to the 3x, and once you you don't really need the chain rule for this, but just to demonstrate how it works, e to the x is a function, 3x is a function, so we're going to take y is equal to e to the u, and u equal to 3x. So you see we've not changed anything here because that's still the same function. And then dy by du is equal to e to the u. Du by dx is equal to 3. Now we look at this rule, dy by dx, which is what we want, is equal to dy by du multiplied by du by dx. So dy by dx is equal to 3 e to the 3x. And you can use this for more difficult examples, but that was just to demonstrate the point. Now for the product rule, and as the name suggests, it's useful when two functions are multiplied together. We're going to write this one down in a slightly different notation, d dx, and this, because this is our function y in terms of f of x multiplied by g of x. That would be our y, so this is equivalent to writing dy by dx anyway. So that's equal to f of x multiplied by the derivative with respect to x of g of x. Maybe we should go with square brackets, but you live and you learn. And this is added to g of x multiplied by the derivative of f of x with respect to x. This one's definitely better demonstrated with an example. Let's say take y is equal to 2x multiplied by sine x. So we've got f of x is equal to 2x, g of x is equal to sine of x, f dash of x is equal to 2, g dash of x is equal to cos x. And the reason I did those common results before is because then using those common results you can differentiate all sorts of functions using these rules. Right, so now dy by dx, which is what we want, is equal to 2x cos x plus 2 sin x of x times by g dash of x plus g dash of x multiplied by f dash of x. So that's a pretty simple rule. Now move on to finally we'll look at the quotient rule, and if we got y is equal to f of x over g of x, then dy by dx is going to be equal to g of x, so that's the denominator one, put that first, because with the quotient rule the order matters. It didn't with the product rule, really. Minus f of x g dash of x, and this is all over, and we'll go with the square brackets this time, squared. So an example might be, let's think of a good example. Yeah, let's take y equals tan x. I think I did this in the last video, but this is showing you how those common results can help you find things that you actually want to know. And remember, from identities, this is equal to sine x over cos x. So this might actually be a little bit above A-level maths, because I think the function we get at the end a little bit different. But anyway, whatever. F of x is equal to sine x. This demonstrates the point pretty well, so I think it's a worthwhile example. And g of x is equal to cos x. F dash of x is equal to cos x, and g dash of x is equal to minus sine x. Now we substitute that in up here, so we get dy by dx is equal to g of x multiplied by f dash of x, so that is cos squared x, and then we get f of x sine x multiplied by minus sine x, that's minus sine squared x, and we're subtracting that, so that's plus sine squared x, and this is all over g of x squared, so that's cos squared x plus sine squared x is equal to 1, so this is just equal to 1 over cos squared x, which is equal to sec squared x. And if you don't know about these inverse trig functions and these identities, then you can just wait till you learn them at school or college, or you can watch some of my previous videos. Actually, there's some recent videos on these identities, but as long as you can get the idea of what I've done for the quotient rule here, that's all that's required, really. So this is what we call implicit differentiation. So like, it's not in the form y equals, I mean, we could just rearrange this in the form y equals, but just to show the point of what we're trying to achieve here, we're going to differentiate this with respect to x, but when we differentiate with respect to x of y, we have to use the chain rule to get certain results. So first, this is the toughest one, because it's the product of two functions. So we're just going to do the product rule in our head. So first of all, we're going to leave the y as it is and just differentiate the 2x, so that's 2y. Now we're going to leave the 2x as it is and differentiate the y with respect to x. Differentiating y with respect to x is dy by dx, so that's plus 2xy dy by dx, okay? And then we want to add 3, and then again differentiating y with respect to x is dy by dx. And this is essentially all you do. Anything that's not x, if you had a z, a t, or whatever, you just divide that, not divide, you differentiate that with respect, you write dy by dx. Looks like division, it's not division, don't make that mistake I just made. Now we want to get all the dy dx to 2x dy dx plus dy by dx is equal to minus 3 minus 2y, and now we can see that dy by dx is equal to minus 3 plus 2y over 2x plus 1. You see, if we just factorise out dy by dx, we get 2x plus 1, so we can divide by that. And that would be the answer. Well, I'll go more in depth into implicit differentiation, but this was just a view over. I'm assuming you've been taught it and you just need to see this again, just to trigger that memory. So I hope you enjoyed this video. That's everything covered, I'm pretty sure. If I did miss something, please be sure to point it out in the comments, and I'll do a quick video on that. I'll do videos on all the topics in this video in more detail. For those of you that haven't understood this or haven't learned this before or whatever, just would like to see that. I hope you enjoyed. Please like and subscribe, and I'll see you in the next one.